talked about how to solve different types of exponential equations where you can do it mentally, or you have to log both sides and work from there. We've talked about how to solve logarithmic equations, two different types. What we're going to look at in this lesson to wrap this unit up is how we can use exponential equations and logs to help us solve real-life problems, as well as look at a special type of log and a special type of number. But we'll talk about that next time. I'm only going to do some problems today. So just picking from a couple of different career areas, if we look at the business world. So here's the problem. To calculate the amount an investment is worth after a certain time, which we call A, we use this formula, okay? And P represents the principal, or the amount you invest. R represents the interest rate as a decimal. N represents the number of compounding periods, or number of times interest is calculated. So if it's compounded annually, interest is calculated once a year. If it's compounded monthly, interest is calculated 12 times a year, etc. And T is the number of years that you leave your investment in for. Okay, so let's say, suppose we have $2,000. We're going to invest it into an account which offers an interest rate of 7.5% compounded annually. Monthly, pardon me. So we want to answer a couple of questions. And sometimes what I like to do is take all the variables from the formula, so A, B, R, N, and T. 4 of those I'm going to know. One's going to be a question mark. So we invest $2,000. What's that 2,000 represent? P. Interest rate 7.5%. R as a decimal. So 0.075. You can put the decimal point over twice. Compounded monthly. Monthly. For which one? N. N is 12. And if you look at the actual question in part A, how much is in this account after 5 years? What's the 5? T. Therefore, we're trying to find A. So, using the formula, A equals, instead of P, write 2,000, times 1 plus, instead of R, write 0.075, divided by, instead of N, we write 12, raised to the 12, and instead of T, we write 5. So this is pretty straightforward. This is just a calculation. You just have to make sure you do it in proper order of operations. Okay? So I'm just going to simplify 12 times 5 first, and then I'm actually going to do the whole thing on my calculator. Okay? What would you do first? Sorry? The division in here? So, because wouldn't we have to like find the sum of these two? So we divide this first, add 1. Okay? So 0.075 divide 12 plus 1. We should be sitting at 1.00625. So this is 1.00625. What do I do next?
Add 1.
I've already added 1. Raise it to the 60th before we multiply. So raise it to the 60th and then times 2,000. And remember, we're dealing with money, so you automatically round to 2 decimal places. So we should get an approximate answer of $2,906.59. Okay. Okay. That's pretty straightforward. This one is going to require a little bit more work, or knowledge of what we did in this view. So again, A, P, R, N, and T. Well, P doesn't change, or sorry, P does, no, it doesn't. Still 2,000. The interest rate is still 0.075. The compounding periods is 12. Okay. What does this represent? A. So that's the question mark. And notice that unknown is in an exponent, which means it's an exponential equation, which means we're going to have to use logs to help us. So instead of A, 4,000 equals, instead of P, 2,000. 1 plus 0.075 divide 12 to the 12 times T. Well, I've got to get rid of all this stuff and get T by itself. Okay? Well, the first thing I'm going to do is I'm going to simplify this. And I believe it was 1.0065. Okay. What might you want to do next? Sorry? Divide both sides by 2,000 to get the power by itself. So we get 2 equals 1.00625 to the 12t. We now have an exponential equation. Obviously, I can't make the basis the same mentally. Okay? So now what? What did we do yesterday when we were here? Sorry? Log both sides. Because when I log both sides, I can use one of the log laws to bring the exponent in front of this log. I want to get it out of the exponent. So it's going to be log 2 equals 12t times log 1.00625. Well, how would I get t by itself? Actually, I could divide by 12 log 1.00625, right? Because wouldn't it get rid of that and that? You could do 2 divisions, that's fine. Okay. So therefore, to get my answer, log 2 divides 12 log 1.00625 is going to be my t. And this, oh yeah, okay, so let's say 1 decimal place. Anybody got it? 9.3. And remember, that's years. Good. Yep. So that basically told you how long it took to double your money. Right? Which a student in the essential class would be able to tell you actually without having to do all that work. Just saying. That is true. That's very true. Right? Just like essential students know this.
I put 3 years to say it.
Okay, this is the kind of stuff we do in that course. Depreciation. It's the it's when some sort of object loses value. Okay, what kind of things lose value over time? Cars, house. Generally, they go up. Okay. A what? A boat, yes. Used car, clothes, used clothes, yes. Yeah, you could probably say clothes depreciate over time. Or do they come back and actually, because they become vintage, they actually go higher? I guess so, yeah. Can you think beyond? Can you think in one of your courses something that depreciates over time? In one of your courses?
Biology.
Biology? What depreciates in biology? Thanks for sharing. Laptops? Yeah, probably, yeah.
I don't have my knowledge.
I suppose. What? Really?
Not this class. The what? I'm just.
Some, what some might appreciate?
Yeah, make one.
Okay. How about chemistry?
Nice.
Yeah, shelf life of chemicals, right? Depreciates over time. Okay. Anyway, we're going to talk about vehicles. We're going to talk about cars. Okay. This is a general formula for depreciation. The value of the object, in this case it would be a car, is equal to how much the object was worth when it was new, times 1 minus a rate of depreciation raised to the time that it depreciates for. Okay. So let's say you purchase a new vehicle, costs $17,500, okay, depreciates at a rate of 16% a year. That's a little low. Generally, they depreciate a little higher than that. Okay. Anyway, what would be the value of the vehicle after 4 years? Well, we've got three variables. We're trying to find the value, so that's the question mark, which means the other ones we must know the numbers. Well, the principal is 17,500.
The rate of interest as a decimal is going to be 0.16. And since we're finding how much the value is after 4 years,
T is 4.
so this one is going to be a straight calculation, just like the previous example, part A. So 17.5 times 1 minus 0.16 raised to the 4th.
So we could do this all in one shot.
Do this, raise it to the 4th, times this,
Because it's money,
2 decimal places,
so that's going to be 0.84 raised to the 4th times 17.5. 87.12.75. Okay. So about half its value. Okay. So after 4 years, if we assume that depreciation rate, it's going to be worth about half what you paid for it.
another type of question that could be asked.
How long to the nearest year, which means T is our unknown,
Which means B is going to be 3,000, because we're trying to figure out how much time does it take for B to get to 3,000. B is still 17.5. R is still 0.16, and T is the unknown. So, using our formula, 3,000 equals 17.5 times 1 minus 0.16 raised to the T. Well, simplify the parentheses first. Zero 0.84.
then what?
Divide by 17.5 to isolate the power.
And so 3,000 divides 17.5 gives us a pretty long number.
Let's go
3 decimal places, which is what we should usually be doing.
equals 0.84 to the T.
Now what?
Log. That's it. That's it. Now that both sides are in log form, that allows me
To pull the T as an exponent in front of the log on the right-hand side and turn it into multiplication.
So log 0.171 is going to be T times log 0.84. And then we just divide log 0.84 to get T by itself.
And again, we'll go 1 decimal place. 10.1. Seems to make sense. Because it took 4 years to go to about half its value. This is going down even further, another 5 grand, over 5 grand more. So you think it would take well over 4 years, which 10 is. Okay.
All right. The science world.
Yay. Don't worry, it's not going to get too crazy. The measure of acidity of a liquid is called the pH. This is based on the amount of hydrogen ions in the liquid. The formula for pH is negative log and then amount of hydrogen ions, negative log of the amount of hydrogen ions. Or sorry, negative H plus, where H plus is the concentration of hydrogen ions in moles per liter. Okay. So if the concentration is 0.02 moles per liter, what's the pH of lime juice? Well, we're trying to find pH, so that's our question mark. And we are told this, it is 0.02. So it looks like we got just a straight calculation. Where to find the pH of lime juice, we're just going to go negative log 0.02. And then we want to go to 1 decimal place. Okay. What do we get? Sorry? 1.7? Thank you. 1.7. Next one. A lake affected by acid rain has a pH of 4.4. A person suffering from heartburn has a stomach acid pH of 1.2. How many times greater is the hydrogen ion concentration of the stomach than that of the lake? Well, don't we have to find the hydrogen ion concentration of both first before we figure out how many times bigger one is than the other? Okay, so we got acid rain. And I'll just say stomach. So using that formula, we write it here. Well, this time, I know the pH is 4.4. I don't know the hydrogen ion concentration. Similarly, I won't write the formula again. This time it's 1.2 equals negative log. Well, this isn't an exponential equation, so we're not logging both sides here, because one side is already logged. What's that?
It's like 10 times.
Right.
Yeah.
So you have to change it to exponential form. So 10 to the 4.4 will equal the hydrogen ion concentration. I'm not going to write that out using digits because I'm not asked, that's not my final answer. This one is 10 to the 1.2. Oh, sorry, wait a minute. Wait a minute, wait a minute, wait a minute. Go back first here. Because I forgot to address something. What did I forget to address? The negative. So what should we do? Right. Okay. So this is going to become. I knew there was something wrong. Put it in that form. It's going to become this. So therefore, it's going to be 10 to the negative 4.4 is equal to the hydrogen ion concentration of acid rain. Similarly, here I'll just jump. It'll be 10 to the negative 1.2. So I am asked, how many times greater is this than this?
How would you figure that out?
Yeah, divide, right?
Like how many times bigger is 20 than 2? 20 divide 2. How many times bigger is this than this?
This divide this.
Remember your exponent laws?
When we divide two powers with the same base stays the same. And what do I do with the exponents? Subtract. So it's negative 1.2 minus negative 4.4. Therefore, it's going to be negative 1.2 plus 4.4.
Just 3.2. And you can leave it like that. You don't need to change it. So that would be our answer. So that's an example where we had, it wasn't an exponential equation we ended up with. It was a logarithmic one.
This last one, kind of similar. Earthquakes. Okay? So we can measure the magnitude of an earthquake on the Richter scale by using the formula log of A over A0, or A naught, where A is the intensity of the earthquake and A naught is the intensity of a standard earthquake. Okay? So we're told an earthquake in Vancouver has a magnitude 6.3. An earthquake in Japan has a magnitude 8.9. How many times more intense was the Japanese earthquake? So we need to find the, we've got the magnitude, we need to find the intensity of Vancouver and the one in Japan. So using the formula, I know that for Vancouver, the magnitude was 6.3. I am trying to find A. For Japan, the magnitude was 8.9. Again, I am trying to find A. But I need to deal with this A naught thing. Like technically, I can't find the intensity unless I know this, right? But if you think about it, we're trying to find out how many times bigger this is than this. Because each of these is being divided, or we're dividing the intensity of each of these by A naught, they're going to be the same, right? So really, they become irrelevant. It doesn't matter. It matters if I want to find the intensity of Vancouver or the intensity of Japan, but I'm not finding those. I'm finding out how many more times more intense this is than this. So I don't need these. So I can just say that this one is going to be 10 to the 6.3. And this one is going to be 10 to the 8.9. And all I want to figure out is how many times bigger this is than this. So once again, if I want to find out how many times bigger something is than something else is, I take that first one and divide by the second one. And I get 10 to the 2.6 using my exponent law, division exponent law again. That's it. So like I said, this becomes irrelevant
only if I'm comparing the two. If I actually wanted to find the actual intensity, I would need to know A naught. Okay. Okay.